So, hi everyone, and thanks for turning up for the first lecture of the day. Waking up early and coming, but yeah. So, I'll pick up where I left off, and start continue talking about parameter estimation in general first, and then specialize to gravitational wave sources. And so, I really like these huge blackboards and the opportunity to use them. But the side effect is that you're always a bit slow, right? So then I thought that I could sort of do like something like a mix, like at least, yeah, yeah. So, but I thought I could cheat and act, this is like slides. So I just came 10 minutes earlier and wrote these equations. These are all equations that I wrote in the last lecture. So none of it is conceptually, should be conceptually new for you, but I'm just writing it. I just wrote it here so that I don't need to spend time writing it again, right? So I'll just go over quickly, right? So we first set up the framework of inference, right? So it's typically called Bayesian inference, but the way I defined it in the last lecture, it is frequentist inference, right? In the case where the signal whose parameters you're trying to estimate is a fair draw from a population of signals out in the universe whose parameters in the population are drawn from some prior pi or p, right? And all the other things in the equation are things that I defined, like the model parameters, like for the binary black hole case or the binary merger case, it would be like masses, spins, etc. Maybe if you have neutron stars, there's more interesting things like tidal deformability and maybe more things, right? And then the data is all the data, right? So if you have however many detectors, the union of all of the data is the data set, right? And then so the left hand side is what is called the posterior probability distribution, which is under the assumption that the thing that you're picking is a fair draw from the population. Then what is the implied distribution for the unknown model parameters given the data that you saw, right? And then, so this is general, right? And then to make progress, you have to define the likelihood, which is, like use case specific. In our case, right, it's not even fully known, but we have a model for it. So the model is that, the data in the detector consists of the sum in each detector, like consists of the sum of a signal, right, whose a signal is h of, I've written it as h of t given theta to emphasize that it's a time series and it has a set of parameters that label it, and then the residual is the noise. And really, the theta in that equation should be like theta true, right, which is unknown. And then you have a likelihood for what the noise is. So if you knew theta true, you would have, you would know what the noise is, and you don't need to do any inference, of course. But when you don't know what theta is, right? So then the likelihood, you it's conditional on the true thing being theta. Then it's the Gaussian model. So I straight away wrote the log likelihood because the Gaussian model has an exponent. So I wrote the log, and the log is a quadratic term. Right? So there is a prefactor, the c, which is the normalization constant, which is not going to be important for us, and a quadratic function of the residuals or the noise with like with sigma inverse sandwiched in between, where sigma is the covariance matrix of the data. So so if the data is instead of a continuous thing for which this would be a measure, right? So for a or some operator. So when you have a finite dimensional thing, operators become matrices. So sigma becomes an n by n matrix, and sigma is a symmetric positive definite matrix. And in going from the first equation to the second, all I've done is I've expanded the square, and there's a term which involves only d, and I just absorb that into the C because I'm interested, the data is given, you're not varying the data. So it's not important in terms of the dependence of this function on theta. And then this is the sum of two terms. So the first term involves the data. So it's like the overlap of it's like an inner product, kind of like an inner product, because this is a symmetric matrix. So it's the inner product between a vector, which is like, this thing as a column vector, and transpose becomes a row vector, and then the data. So this is the only thing in the entire process which will require the data, right? And this thing here is the signal only piece. So this is general again. So the sigma could be any positive definite matrix that you could dream up, but the something that is maybe like a closer model to reality. I mean, it is not perfect, but it is, it makes our life easy, is that we assume that the noise is statistically translationally invariant. So that means that the correlation function of the noise at two different times, right? So so this would be some entry of this matrix, and the correlation function is only a function of the lag. Or in terms of this matrix, we saw in the last lecture that means that this matrix is a Toeplitz matrix. So it is constant along diagonals. And in fact, it is symmetric. So only the upper part carries some information and the lower part is the transpose. And equivalently, we can describe the covariance, so this C of tau, which is the autocorrelation function, in terms of its Fourier transform. So you take this C of tau and integrate it against 2 pi I f tau, right, and with d tau, and you get a function of frequency. And this function is called the two-sided power spectral density, right? And under the condition that the data is real valued, right, and this autocorrelation function, so, and there is no like forward and backward directions in terms of the noise. So then this is a function of only mod tau, and that makes S also even and real valued. And so you can just sum S2 of f and S2 of minus f and call that S of f, right? So that is the one-sided power spectral density. And this is really the mathematically rigorous definition of this. And this is like a shorthand people use, which is, so because the thing is, this n of f is not a mathematically well-defined quantity because the noise is not square integrable, right? So, and that is reflected in the fact that the variance is infinite at f equals f prime. Okay, and then we started talking about some signal processing stuff, which when I came to the school, I actually did not plan to talk about signal processing, but it just happened to be that, and I'll just continue, right? So because it's a very essential process in time series analysis of any kind. So here, I'm going to assume throughout here that the data is sort of regularly spaced. Right? And I got a question after the last lecture saying, what happens if it is irregularly spaced? And of course, it becomes much more complicated, but we'll live a simple life here. Right. So now one of the fundamental operations in, when you take data and actually map it to what you observe, is you window the data. By that, because you don't observe the data at all times, you observe it in some section of time. And you might choose, even if you have data elsewhere, you might choose to analyze only this section for whatever reason. So then that is implemented by multiplying it with some window function, which is a function with compact support, right? And a simple window function is a box, right, which is 0 and 1 and 0. But you could have more complicated window functions for whatever purpose you might want. And in multiplying with something in the time domain corresponds to convolution in the frequency domain. So then in the frequency domain, the Fourier transform of this data will be the convolution of the Fourier transform, the Fourier transform of the window data is the convolution of the Fourier transform of the data and that of the window function. And for example, if you have a box function, right, so the Fourier transform is a sinc function, which has like 1 over x states. So then it tends to broaden any sort of noise significantly. Okay. And then I talked about sampling, which is a very important operation, right? Because, even though the underlying noise in the detector is, truly continuous, but we don't really work with continuous functions because, we store floating point numbers at some, finite cadence in our detector. So typically it is sampled at some time interval, which is why there was a column vector, right, up above. and the sampling is happening at an interval of delta t. And in the last lecture, I defined, I talked about how to think about what this sampling is doing mathematically. I said that you can think about the sampling as you're taking the underlying continuous data and multiplying it with what is called a Dirac comb. And Ariel helpfully pointed out that there is a pre-existing symbol for the Dirac comb, which is actually a very nice symbol. So I'll write it. So I'm going to represent, d delta tt to be like the thing that has been sampled at delta t, and that is the product of the underlying continuous d of t and this symbol. Okay. It's called the Shah symbol, and it's obviously very well suited for the purpose. And so this Shah has a parameter which is the sampling rate. So it's a function composed of a bunch of Dirac delta functions, and this Dirac comb has a remarkable property that its Fourier transform is another Dirac comb. So the Fourier transform of the Dirac comb is a Dirac comb in frequency, so 1 over delta t, a Dirac comb in f at a rate at interval 1 over delta t, which is called the sampling frequency. Okay. So now given this, we know that multiplication corresponds to convolution in the Fourier domain. So that implies that the Fourier transform of the sampled data, so I'm going to represent it by this symbol. The delta t is again the sampling rate, and the tilde is the Fourier indication. So this is the convolution of d and f. Just give me a second. Yeah.
The Dirac comb, only the spacing is the period, and not the sampling frequency. So the sampling frequency is the largest frequency.
No. It's the sampling frequency. There's no other period in the problem. Okay, good. So this cryptic notation, I also diagrammatically showed what it indicated. So if the original D has a Fourier transform that kind of looks like this, so this is D tilde as a function of f. So the convolve thing looks like you're taking this and you're having a comb and you're running this over the comb like this. And that means you produce many copies of this, right? So you get something like this, something like this. I've made it much broader than I drew it in the last lecture, but it's just a parameter choice. Oops. Okay. So each of these peaks is separated by the sampling frequency. Of course, what you see is not like all of these curves, you see their sum, right? Because the convolution is like the sum. So this is the sum of the Dirac delta. So this will be the sum of all of these. You actually only see this thing. So you only see the red line. And the point I made in the last lecture is the map between the white curve and the red line is not one-to-one. And to see why, you can consider a simple example. Consider another function whose Fourier transform looks like this. So it only looks like it's 0 outside and it matches the red curve here, right? So the repetition of that, the summation does not lead to anything because they don't overlap, and that gives the same, like pink curve. So the map is not one-to-one, so you lose information. In the special case where this orange thing, right, it lives only inside this interval, then it is invertible because if you knew that, because then you would just read off the value in this interval and repeat it forever, right? So that is a sort of a proof, if you like, of the sampling theorem, which says that a band limited function, right? So a band limited function, which is this function, right, which has a continuous time series, can be can if you're given the orange, so the pink curve, which has the same information as the discrete samples, the underlying function can be completely reconstructed with zero loss of information, right? So that is called sinc interpolation sometimes. Okay. There's also another word for this whole thing. So it is sometimes called the periodic extension of this thing. So you take this thing and periodically move it and then add them, right? So it's sometimes called that. Same thing. So this interval, right, within which it must be band limited for the sampling theorem to hold has a special meaning. So the width of the interval is the sampling frequency. So if I set 0 to be the center, right, so then there is a special frequency which is called the Nyquist frequency, which is 1 over 2 delta t, half of the sampling frequency. So if the signal has power only within minus f Nyquist and f Nyquist, right, so it can be reconstructed. Okay.
Just to make it clear, unlike the signal you know.
Yeah.
So this signal does not satisfy any.
The orange, okay, I don't know what that color is, sorry. Yeah, the orange one is reconstructible. This is not. Yeah. Yeah, if you took the samples corresponding to the pink one, you would reconstruct the orange one by the, by the reconstruction theorem. Okay. Okay. So all of this is sort of, visual, right? So you can also write down what the Fourier transform of this sample thing is, like by expanding this, and you get that this is okay. So this is called the DTFT. Right. So this operation is the Fourier transform, which is defined on the full line, right? And this is DTFT, which is defined for sampled functions. Okay. Good. So I talked about the effect of sampling and I talked about the effect of windowing, but in reality, you do both, right? So you observe data within a finite range of time and you also sample it. So what you get something that, so data is windowed and sampled usually. So I'll write this as dw delta t of t, saying that this has been windowed and sampled. And this is d, so first windowed and then it has been sampled. So use the SHA symbol. So this is d window d of t, window of t, of t. Right, so the data you are ever going to analyze is actually going to be this thing, right, not d of t. And that has some consequences. So let's see what that means. So let's take this sample thing here, right, the same thing I drew here, except now, so you have something and then there is zeros outside, right? So this is data that has been, so this is the interval that it is being analyzed within, right? So there is a t. So there is a duration now, t, which is n times delta t, where n is the number of samples. And the spacing is again as before, delta t. Okay. Okay, so now I want to know what is the Fourier transform of this windowed and sampled data. What does it look like? So d windowed sampled this thing. So this is, so if I just take this formula here, right? So the dtft is, I'm just going to plug that in, except the infinite summation in the dtft is going to be replaced by a finite summation over the things that are non-zero. So that is going to be summation n is 0 to n minus 1, or like 1 to n, whichever way you like to index your thing, dw of n delta t. Okay. Right. And from the definition here, right, you can also see that this thing, this whatever this thing is, this is, if you look at the first equation here, right, this is the product of these two things. This is going to be the convolution of those two things. So this is going to be 1 over delta t d window convolved with Risha at the sampling frequency f. Okay. Okay, I mean, it looks really like formal and boring, but I think it's useful to go through this at least once in your life, so I will do it, and there'll be a reason for that. Okay, so this is the Fourier transform of d, let's say, so the continuous d. So now the dw, right, so the windowed one, it has a tail because of this thing, right? So it looks like this, and then bad stuff happens, right? And then so the orange one is going to be repeated because of this operation. So it's going to, so instead of that curve, right, that now I'm going to have a curve that okay. And what was, please ignore the varying degree of overlap of this and that in that figure. But the point is, so if it were just the white curve, it might look like this. But because it's the orange curve, right, so that thing is going to look like. Okay. The orange curve is purely windowed. Yeah. So I'll write that. Yeah. Good. Okay. So this is some, so now I want to describe the pink curve. Okay. And how do we do that, right? So the pink curve is the Fourier transform of these dots, of the pink dots. And now we can use the Shannon sampling theorem in reverse. Right. So just like a band limited function can be reconstructed from samples, a duration limited function can be reconstructed from a subset of the frequencies by sampling in frequency. Right. So instead of looking at the full continuous pink curve, I'm going to just, first of all, the full continuous pink curve, I only need to describe it in this region. And then I only pick special points. And everywhere in between, I can do sinc interpolation and get it, because it is the Fourier transform of it, like something that is duration limited. I'm basically using the fact that Fourier transforms and their inverses are both, like they'll have the same form. Okay, so that means instead of, so let's say this is f equals 0, and this is the Nyquist is 1 over 2 delta t. Okay. So now what is the spacing of these frequencies, right? So the spacing of these frequencies, you can argue just like the spacing of the times determine the frequencies, right? So the spacing of the, sorry, just like there is a Nyquist frequency, you can imagine that there is a Nyquist time. Right? So the Nyquist time, 1 over 2 times the total time, right? So t over 2, that is this thing, half of this must equal half of the sampling rate. So let's call this delta f. Okay, this is very bad. Right, so we get delta f is 1 over t, right? And just like we wrote down the Fourier transform there, right? So the dtft, you should be able to do it here. And I'm going to write that. So I'll write it somewhere. Okay, good. So now instead of a continuous frequency axis, or did I say t? Sorry, has to be f. Bruce is not watching me like a hawk today. It's okay. Okay, so instead of a continuous frequency f, I'm going to only now require it at the discrete frequencies here. So that is, I'm going to write this as m delta f, which is m over t. Right, so this is summation. So now n equals 0 to n minus 1. Okay. So this whole thing is basically m times n divided by uppercase n. Right? So this is now, instead of an infinite sum, this is a finite sum. So this is relating the finite number of sampling frequencies here to the finite number of data points there. Right? So this is called the DFT instead of, so Okay, so we started with the ft, which is a mathematical operation that is useful but not done on a computer. And then we went to the dtft, which is better. It's discrete, but it goes on forever. And then we went to the dft, right, which is finite on both cases. But then there are all these effects that happen. Okay. And just like the Fourier transform had an inverse, so the DFT also has an inverse, which also looks like a DFT, which is not surprising because frequencies and times are like they're you can replace frequency with time and everything carries through and everything is a regular grid. So I'm just going to write it down. W delta t of n delta t. So now there is a 1 over n. So here I'm going to take m to go from minus n over 2 to n over 2 minus 1. I mean, if you do it in Python, it would be like n over 2 minus 1 if it is even, or and something else if it's odd, but okay, fine. Lot of there are a lot of formulae on the board, so if something I wrote is confusing, please ask me. Okay, good. The
Is that something right in the frequency when you introduce?
yeah, m is the index, so this is m equals 0, n over 2. Yeah. Yeah. Okay, good. Right, and it's important to have these because these are the things we actually work with, right, when we do data analysis. So now I told you what is the autocorrelation function, what is the distribution of the Ds, right? The distribution of Ds is just given by the likelihood, right? Good, right? But so then if you only worked in the time domain, right, you would not need, all of this would be a curiosity, you would not need to do any of this stuff, right? But in the frequency domain, right, so the continuous Fourier transform have this nice, covariance function. So now the question is what is this distribution of these twiddle D, the windowed and sampled ones, right? And so first of all, right, I mean, there'll be some details, but before the details, you will immediately be able to figure out that it is some Gaussian, right? Because ultimately these D twiddles are all linear functions of Gaussian variables. And any linear function of Gaussian variables is Gaussian distributed. So there will be some other like covariance matrix. Instead of covariance matrix here indexed by times, you're going to have a covariance matrix indexed by the frequency index M, right? So the question is, this is the question. Okay. So I'm first going to write down the answer in the time domain, right, which is easy, right? Because these windowed ones, the sampling does nothing. It's like, just the D at that time, right? And the window, right, is just being multiplied here, right? So that means in the covariance matrix, so if I take the these guys, right? Right, so they will have a covariance matrix, which is there are n of these guys. So there will be n of them, but the covariance matrix will be like this. Okay, I'm just going to write it down. Sigma of these guys is going to look like W1, Wn, bunch of zeros, and then the sigma of the p's times W1, Wn, 0, 0. Okay. So this is just going to be a this same old matrix that I had here, right? And I'm going to multiply by W by this on the left and on the right. And what that is going to do is to make, so this matrix which had this nice Toeplitz property no longer has that property, right? So now it is no longer constant along diagonals. So this guy along diagonals, it, if I plot it, it might look like this. I don't know. Okay. So what is the covariance matrix of this nasty thing? And I'm just going to write down the answer. I'm not going to subject you to the derivation, but it is, you can very easily see it from what I wrote. It is just in mathematical form. So I'm going to write that. So now the twiddles, right? So these tildes, right? So Fourier transforms, they are complex valued. So okay, so this is I'm going to write down the answer. So TF S of F W twiddle okay. It's going to be this expression, this kind of a beast of an expression. So let's understand what it means. So I'll just show what it like the, so this is an integration, right? So f is a dummy variable that is being integrated over, and the legs that are sitting outside are fm and fm prime, right? The discrete frequencies. And so let's see. So for ground-based detector like LIGO, right? I already drew the s. So as a function of f, this is going to kind of look like this. Okay. Right. And this is set by the noise processes. So there are a few, like as many as you want lines in the data. And there is this underlying continuum, which is, so there is some, so you can ascribe things to various causes, but, it's only like sort of indirect, that you could say that, maybe this is because of seismic noise or, like some radiation pressure in the mirror, and this is because of short noise, right? It could be because of many things, right? So this is S of S. This is this guy in the integrand. And now there are two other things being multiplied. Okay, so let's see what they are. So there is this, okay, I think one of them has a complex conjugate. Yeah, if it is on the other side, don't blame me. Okay. It's an exercise to see which one has the complex conjugate. Yeah. Oh, thanks. Did I? Oh, really? Yeah, thanks. That was stupid. Yeah. What? Where?
Your expectation about
Right. Thanks. Okay. Good. And so now this is a dummy variable f, right? I'm interested in the thing evaluated at some discrete frequency fm and fm prime, which lie on this grid. So there is one fm. So let's say that this is fm. And so this is the windowed and sampled window functions Fourier transform. And we know what that looks like. So this guy, right, is going to look like okay. So there is this green curve so this green curve is remember, it's the periodically extended Fourier transform of W, right? Just like that, right? So you take the Fourier transform of W and shift it infinitely many times by the sampling frequency. So this is Fs is 1 over delta t. Okay. So this is F sub m, this is going to be F sub m plus Fs, and so on. And this guy, let's say this is Fm prime. So same story, it's going to look like that. Okay, peaks again separated by Nyquist. Sorry, by the sampling frequency. So it's going to be this nasty thing. So what is this thing? This thing is saying you take the product of the white curve, the green curve, and the pink curve, and integrate, do the Riemann integral. And you can immediately see that this is very worrying, right? Because this blows up here, right? And I don't want that, right? So this means that if you do it this way, it's going to cause you like basically blow up your covariance matrix. So this is not a good thing to do. So what do you do in order to cure this? So what do you do is, so this is the S of f of the underlying continuous data, right? Which, and all the noise processes. And this, like this Fs, right? This delta t is telling you the sampling, right? So what you have to do is you have to, before you sample the data, you have to band pass it. You have to apply a low pass filter. So what's a low pass filter? It is something that kills high frequencies, because otherwise all the short noise at very high frequencies is going to basically like be reflected in the covariance matrix of very low frequencies. This phenomenon is called aliasing, right? And this will basically make your data non-informative about anything because the noise blows up. So what do people do, right? So before they sample the data, right? Before you take dot, 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 right? What you do is you apply a low pass filter. So the low pass filter is something that it's like a window, but in the Fourier domain. So that means in the time domain, it is convolution. So it's like you convolve the data with some small function that sort of walks over the data like this. And then it kills high frequencies. And the convolved, so the band passed or the band pass data will look like this. So let's say, so okay, what's the goal of this band passing? The goal of this band passing is to not be killed by these guys, right? So you have to band pass it well before you hit Nyquist, right? So you band pass it somewhere here. This is actually not too inaccurate. For some reason in the LIGO data, there was a line at 512 hertz, which caused a lot of issues because it's at the edge of the band. Anyway. So this is S of F, and this is, let's say, S band passed of F. Okay. So step one is you have to band pass before downsampling. Okay. And it's band passed and downsampled. So after that, there is only, like only up to, there's only up to F Nyquist. Okay. So if you take like the exercise that Javier gave you on Pumble or on Git, you can download data from LIGO, which is, I don't know, you can choose a sampling rate. They have a choice of 1024 hertz, 4096 hertz, and 8192 or 16384 hertz, right? And if you take each of them and pass it to some routine to measure the power spectral density, you will get something that looks like this, and then it falls off and goes to zero. Right? And this is not because the noise is going to zero. It's not because the detector is awesome there. It's because you applied a band pass filter. Right? So that's something to keep in mind. And I'll explain how that causes problems later sometimes. Okay.
There is one factor
What?
outside the integral, by Ekman.
That is because you're talking about some where it was for, yeah, so I'm absorbing that into the window function.
And there is no star.
Okay, I will trust you. Okay. Sure. I guess the window function there happened to be real valued in the Fourier domain. Okay. Okay, good. Okay, so now that's the first thing. The second thing is we are going to assume, so remember that in the, really the thing that was periodically extended was not the white curve, it was the orange curve that has been broadened, right? So these guys are very nasty, and if you pick any time thing here, you would get a contribution from this guy, this guy, this guy, and so on. And they're all suppressed very weakly, so they will all add, right? So we are going to assume that that effect is very small. So we are going to assume that the okay, so this 1 over delta t is just to get units correct, because the DFT has the same dimensions as the data, but in the continuous Fourier transform, there is a DF or deta or DF in the other way, so that adds a unit, so that unit is compensated by this 1 over delta t. Okay, so this is approximating that, this is basically approximating that these guys don't overlap. Okay, so the periodic extension is just taking the primary thing and repeating it without overlapping it. And when is that justified? So this is equivalent. So this is equivalent to the assumption that t is much, much larger than delta t. Okay, why is that? Because the spread of this is like 1 over t, the the window duration, and this gap between this is like 1 over delta t. So you want 1 over t to be much smaller than 1 over delta t, so that t is much larger than delta t. Right, so this is the second assumption. Okay, and the third assumption is we are going to assume that the W tilde of f, right, is sharply peaked around f equal to 0. So it's almost like a Dirac delta function, right? But it cannot literally be a Dirac delta function because I just told you that the width is related to the sampling interval t, right? So the width is 1 over t in frequency. So now I want to know what is the height of that thing, right? And for that, I'm going to use Parseval's theorem, right? So Parseval's theorem says that the power in frequency domain is equal to the power in the time domain. Okay. So if the height is h, so then this is like h square times the frequency width is like 1 over t. And this thing, if the window function is order unity for most of the like the length, which is not bad, so then this just becomes t. So this says that the height h is approximately of the order of the time, okay, which is n delta t. Okay, good. Okay, and we still are not done. We need a fourth assumption. So the fourth assumption we are going to make is that S of Fm is approximately S of Fm prime. So this is equivalent to at order of magnitude level, right? So this is saying that the PSD is not varying like crazy, okay? If that happens, then the PSD is just some constant that comes out of this integral, right? It's just some slowly varying thing. And it is dominated by this sharply peaked Dirac delta function type things. So that is going to finally enable us to, under these assumptions, I'm going to be able to write the covariance matrix. Is approximately, so half times S of Fm, that's this thing. So the delta F, the width of it is like 1 over T. So that's the dF part. And this thing is going to give you two factors of T because the height is T. And you need a 1 over delta T square because of the units of the discrete Fourier transform. And then a delta M prime. Okay, almost there. So where am I? T. So this is, so T is n times delta T. So I'm going to take out the T here. So this will be n over 2 delta T S of Fm Dirac delta of M prime. Okay. So it took us some time, but we derived equation 2 of most reviews of parameter estimation, right? So this is called the Whittle likelihood. But you can see that it has so many assumptions buried inside that are often not satisfied, right? You just write this and then pass it to a code that you like, Bilby or whatever you like, right? But this is what is happening under the hood. And okay, where can it go wrong, right? So the thing that obviously, you have to remember that you bandpass before downsampling, otherwise this is crap, right? And so you have to do that. The second thing is, the sharply peaked stuff, you have to just assume that you have to use enough samples, and then this part, right, where the power spectral density is not varying too badly, that is really bad here, right? So you have these lines in the data, and these lines are several orders of magnitude above the floor, like 2 to 3 easily, right, many times. So that means that this assumption is very badly violated, okay? So here I wrote down this covariance matrix, and this covariance matrix under the identity assumption, okay, it depends on how you write it. Okay, I'm going to do it this way, okay. So it kind of looks like this, right? So it is something along the diagonal and 0 elsewhere, right? But if you actually take the data, right, and evaluate the covariance matrix, even if you bandpass it, you're going to have, first of all, some spread here. And second of all, wherever there are lines in the data, you're going to have these star-shaped things. Okay. Okay. So, and what is the Whittle approximation is ignoring all the off-diagonal terms and just setting the diagonal term to whatever it is. And this, so people talk about, detector miscalibration, or so this actually causes errors at the same order of magnitude, right? So if you are like interested in ultra precision tests of JR, I don't know, like your goal in life is to do that, right? So then if you are at the level where you have to worry about detector calibration, you also have to worry about this. Okay. Sorry, I took a very circuitous route, but hopefully even the experts in the audience got something from this. Good. Okay, so now, okay, I'm not going to write it down. So, right, so this likelihood, okay. So this is the covariance matrix, right? So the likelihood is going to be a quadratic function of this n instead of d being n, right? So it's going to be, here it's a quadratic function of, like the residuals with the time domain covariance matrix inverse. And now in frequency domain, it's going to be the same thing, this guy with this guy on one side and this with the other side, and the inverse of this matrix in the middle, right? If that matrix is an identity matrix or a diagonal matrix to be more accurate, you can invert it, it's trivial. But if the matrix is has all these nasty stuff, then you have to invert it numerically or use some fancy procedure to do it. Okay. Any questions? Yeah. So before all the approximations, it's the same computation time, right? Because you're just changing bases in a sense. After the approximations, this becomes much faster because it is order n instead of order n square. Yeah. So that's why it is the first equation in all PE reviews. Yeah. Okay. Okay, so now the log likelihood function of d twiddle given, or d tilde given theta, right? So this is again some c of d, right? Like here, right? It's just something independent of the model. And I'm going to write it down here. So it is going to be real part of summation m greater than 0. So under the Whittle approximation, right, so without the nasty covariance matrix, it's possible that this minus is a plus. It must be so. Okay. Okay. So like just like this looks like the, like some quadratic function, right? One involving the data, one without the data, right? And this motivates the definition of an inner product. Okay. So an inner product here between some arbitrary A and B is like this thing, right? With D going to A and H going to B. Okay. So now this is the discrete version of the inner product, and you can sort of close your eyes and extend it to a continuous version with the kind of approximations we have done under Whittle, right? So that they are much worse than this. And this thing looks like 4 times the real part of 0 to f max df a tilde of f star b tilde of f over s of f. Oops. Okay, so this is like if this is acting as if instead of A being a discrete thing, it's a continuous thing. But in reality, this thing is sort of mathematically nonsensical because we apply it with D being the A being the data and H being the signal, right? B being the signal. And neither is really square integrable, right? So the data goes forever and the signal also goes forever. Maybe it stops when the black holes were assembled first. But that's before we were all born. Right? So it's none of these integrals, like they really, like this A tilde of f, B tilde of f, they are not well defined. Right? But what makes them well defined is this 1 over S of f. Okay, and I'll show why, right? So it's conventional to take this 1 over S and break it into 2 parts, 1 over square root of S here and 1 over square root of S here, right? So then it looks like a symmetric thing, right? And this 1 over square root of S is called the whitening filter. Okay, so you can think of, remember, right, 1 over, there is some function of frequency, right? Multiplying in the frequency domain corresponds to convolution in the time domain. So if I take the filter corresponding to 1 over S, so that filter for LIGO data is going to kind of look like this. This contains the same information as the power spectral density S. Okay, so this is like the time domain version of 1 over square root of S. And you can work out the property, the prefactors of delta t and n, right? And what should we think of this thing as? So this filter is called the whitening filter. And what does it do? So the whitening filter is a filter that, imagine you take the data and then you convolve the data with this mysterious filter, right? You get data that has so convolution is like you can think of this as like a multiplication by a matrix, but the matrix is Toeplet, so it's a nice form, right? But so the convolution, what it does is after the whitening has been done, the data, the noise has been decorrelated. Okay, so before it, the noise has off-diagonal covariance, right? This thing, right? But after you have run this mysterious filter over the data, which you can see in your first exercise, you can figure out the normalization. It's an exercise, right? So you have some data where if you just download LIGO data, right, you'll get numbers which are like, I don't know, the raw strain. If you just plot it, it will be like 10 to the minus 18 or 17, whatever. It's all set by low frequency junk, right? But then if you operate this filter on the data, after that, you will get something that kind of looks like, okay, it's not so regular. I'm very bad at drawing random noise, but it will basically be between like so -5 and 5. You should see it for, if you take 1 hour of data, it will fit like this, right? So because essentially what happens is now it has been decorrelated and whitened. So the frequencies have all been equalized. And now every point, the strain, the whitened strain, if you plot the histogram of that, it will look like a standard Gaussian variable with mean 0, variance 1. Okay, so it's a very useful tool to see, to take colored data, right? Because it is colored data is dominated by stuff that is not really relevant to observations because the S blows up there. And after whitening, it sort of equalizes the dynamic range of all the frequencies. And like the signals, if there are signals, actually they pop out and you have a chance to see it by eye. Though of course that's, seeing by eye is never how you do data analysis, but yes. Okay. But before we move on to, okay, it's like 2 lectures and I haven't yet told you how to get the posterior, but yeah, hope there are like, but this is like an atomic step in that, right? And these assumptions, they carry over everywhere. So, okay, so let's look at some things that come from what we talked. So the first gotcha that often happens is, if you remember the lectures, Matthias's lectures, right? So the h of f kind of looks like this, right? So this is h of f for a binary black hole, cuts off somewhere near the bucket for a massive binary black hole. And if you take a binary neutron star, right, the merger actually happens outside the band, right? So you would have something. Maybe it goes here, but you can't really see it because it's buried under the noise. I exaggerated how bad it is, but not so much. Okay. So now, if you take the data for, I don't know, GW 170817 or 2305, 29, or any of these low mass, very interesting events, right? And let's say that you take data that is, you download data that is 4096 hertz, so sampled at 4096 hertz, with the reasoning that 2048 hertz is the Nyquist. So if you're interested in tidal deformability or something that happens at, I don't know, like 1 kilohertz, right? It's below the Nyquist, so you should be safe. You will, if you evaluate the likelihood using the Whittle formula, right, you will get nonsense many times. You will get like infinities. And why is that? It's because there is this thing that goes to 0 here, right? And it is, you're dividing by 0. And of course, you're dividing by 0 both for the template, after you whiten the data and the template, right? In the inner product there, you should suppress it, but it's never perfect. And often you will get likelihoods that are like garbage, right? And you will not understand why. And the reason is because of this band pass filter. It's too close to where if your thing is a binary black hole, it is suppressed so much that it's not often not very important. But for these guys, you can get artificially, like the log likelihoods can go like crazy, right? And your PE can return garbage. that you run with the code, right? And the way to fix that is either work with higher frequency data, which is, I don't know, download 8192 hertz or 16384 hertz. But then you pay the price of having more frequencies, right? So then you just waste computation time just summing zeros. So then you cut off the sum somewhere where you don't have any more SNR. You can do that, or you can take the 16384 data and downsample yourself without applying this roll-off. You can do a brick wall filter or whatever you like, right? And so, yeah, but this crucial, so if you just take the 4096 hertz for, 170817, this is a thing that can happen and does happen. Okay, good. Okay, let's now, so that's like lesson 1. So lesson 2 is, okay, let's say that, this is all about how to do vanilla analysis of a binary merger, right? But let's say that let's say that your motivation is you want to study ring down. That's your passion in life, right? So now you have a signal that does this. And so there is this part which is in-spiral merger ring down, and you don't want to consider that in your analysis because you don't trust the waveform model for some reason, right? So then let's say you want to analyze only this part of the data onwards, right? That's what you would analyze. Okay, if you were analyzing the whole thing, you put a window somewhere, right, and move on with life, right? The window is not catastrophic for the event, but for this, the window is will destroy your ring down. You will not have any ring down, right? So it will your ability to do the analysis is gone. So then the way to do it is to understand that to go back to the basics, right? You don't need to go into the Fourier domain. You can work with the time domain correlation function. Right? You can just take this thing, and there is a Toeplitz covariance matrix for this thing, and just just do it in time domain, and it will work. Okay, without any funny stuff. There are other ways also, but that's like the most conceptually easy way, right? So the standard way of writing the likelihood, you might not realize that. So getting at it from the covariance matrix in the time domain is definitely useful. Okay, now let's look at a third example where all of this discussion is useful. So like if you follow, like if you followed the history, right? So 170817, right? So the merger that was detected of the binary neutron stars, when it was first detected, right? For whatever reason, there was a ginormous glitch, okay, on top of the data. So if you made the spectrogram of the data, it would just jump out at your eye that this is garbage, right? And it unfortunately overlaps with where like tidal deformability would be there. Okay, so now the question is, how do you deal with that? Right. So there are various ways of you might want to deal with that. So the way, if you download the data today, you will find that this glitch has disappeared, and the reason it disappeared is that like it was found that there was an auxiliary channel which also contained that glitch, and using that they were able to figure out what the thing was and subtracted it without any estimate. It's just they knew what it was. So then that takes away the yellow, and you can do the analysis as you want. But in the beginning, it was not realized, right? So then how do you deal with it, right? So one is like know the answer. Unfortunately, not always true. The second thing is you can use tools like base wave or baseline. So these are like very fancy pipelines that simultaneously infer the parameters of the event as well as the glitch, or do it like one by one in a way that is very 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 finely tuned, very very sort of complicated, and it has been shown that it doesn't like up to whatever degree that people have deemed acceptable, it does not screw with the parameters, right? But so that's another option, right? So this option is to say that I'm going to, try to squeeze every drop of blood out of this. I'm going to try to get at whatever is under that yellow, and then I'm going to, really like model that yellow. Like, I'm going to assume that the yellow is some model, and then use that to fit it out. Right. So that's an aggressive approach. Then that can get at much more, but at the cost of possibly mismodeling the glitch. Right. So that's the trade-off. And the third thing is, okay, you can just say that, I don't want to think too hard. I'm just going to make all of this 0. Right? I'm just going to multiply this thing with a window function like this. And that is obviously catastrophic, right? If you take data, like it's like you're saying that the measurement is 0 here. Right? And that's really bad. Right? I have not seen a gravitational wave signal that looks like that, or yeah, why would noise not be there, right? So that's really bad. And then, so one way of, curing it is you say, okay, my brain is hurting. I don't want to think too much. I'm just going to taper this so that it has a, slightly, like lower effect. And this is like a quick and dirty thing that can be done. And then you can Monte Carlo how much you can taper and not screw up your estimation, right? So this is like Wild West, right? And then let's say you don't want to be in the Wild West. So then you can go back to the time domain covariance, right? In time domain, so there is this Toeplitz matrix. And let's say that the glitch was here. So bad, bad. And then there was good before, good after, good before, good after, okay? And let's say that in the same way, in which in the ring down, you chose not to look at the part before, you could say, I chose not to look at this. It's just like as if, for whatever reason, it tried to save it to the directory, and, the computer had a bug and you lost it. But it's fine. What does that mean? It means that these things are not part of the analysis. So then the covariance matrix is the remaining thing. Right? You can sort of permute this, move this to this side, and then you'll get a block that looks like good before, good after, good before, good after. Now the cost you pay is that this matrix is no longer Toeplitz. You might have something like this, then you might have something like this. And then, whatever madness is happening here. Okay. So this matrix is not Toeplitz. So the D, if like there is no way of Fourier transforming and getting your way out of it. And there are some tricks you can play maybe, but it works. It is logically consistent, and it corresponds to basically saying I ignore the glitch and I'm unbiased by that. Right? And this is the correct thing that you should do if your goal is to ignore the glitch and not model it. Right. So that is another thing that this way of thinking about it might be useful. And often now with lots of events, right, you see that there are like glitches, like a second before or after. And you might say that, okay, second before is not too bad, but remember that the whitening filter has these wings, right? So that a glitch that is a second before will, after convolution, it will spread like this, and it will enter your analysis. So you can either use base wave, or you can say that I can just apply this covariance matrix, and I can just choose not to think about the data during that glitch. And that is mathematically and logically consistent and will be unbiased. Right. So these are all things that if you're interested in these more advanced things in data analysis are useful to have in your toolbox beyond the Whittle likelihood. Right? Because, okay, in the next lecture, I will go a bit more into how the posteriors are actually determined and what you do with them. Right. But hopefully all of, if you're like, if you have never seen this sort of thing before, this derivation was useful. And if you have, right? The assumptions and these, things were useful for you. Okay. Yeah.
I think if you already went so long away to describe what happens when the speeches and stuff, maybe it's also worth mentioning that if it's too slow for you to observe the maybe concerning time,
Yeah.
then you can do the same thing.
Can do it.
Mentioned by 10 volts. If any.
Yeah. So I mean, there is a trick to in certain. Okay. Yeah. So there is a trick to doing this. If you don't want to invert this non-Toeplitz thing, there is a trick to do it in the Toeplitz way. But yeah, you can come ask me after. Yeah, there's some nice linear algebra in there, and that is also a way that you can do without incurring the huge penalty at the cost of. You will have some trouble with the HH term, I think. Okay. Okay.